Just want to give you a heads up in case you didn't look at the line down at the bottom. This video is about twice as long as normal. Slopes are important, so spend a lot of time on it. Okay, here it is. The moment you've been waiting for. The subject matter you've been promised for weeks and weeks. Now, finally, you have it. Slopes. I think I've mentioned before, slopes are important. You're going to use them for a long time, maybe forever. And in fact, you're already using them, even if you don't know it. Maybe you've seen those little yellow road signs, something like that. And it says, how do they write them? They say something like 10% grade. And they're kind of sloppy, so they tend to write off the end of the sign. I'm sure you've noticed that before. That's not me, that's the way they do it. Or it'll say maybe 11% grade or 7% grade. What does that mean? Well, grade is short for gradient, which is another word for slope. It's telling you the slope of the road that you're on. If you're not driving a great big truck, it's probably not that big a deal to you. Well, if you're on a skateboard, it might matter to you since you don't have any brakes. If you see a sign that says 20% grade, I'd jump, but then I'm kind of gutless on skateboards. Maybe you'd like it. So you've seen it once before already. And maybe more than once. So what the heck does slope mean? Let me get my pencil. Okay. Suppose we have x and y coordinates here. X and y axes. Just like usual. Yeah, we have a line. Now this line moves in the x direction and it moves in the y direction, doesn't it? In the sense that you can go from here to here by only moving horizontally and vertically. They probably don't make them anymore, or at least they're probably not so popular. There used to be a game called an Etch-a-Sketch, which had two knobs down towards the bottom of it. Just one way on the left and one on the right. When you turn this knob, I forget which one did which. It's like when you did this, turn this one, the cursor went straight up or down. When you turn this one, it went horizontal, left or right. As it moved, it left a trail, as if you were writing on the screen. Now, by moving these two knobs together, you could move diagonally. Well, that is very educational, actually, because that's exactly what's happening here. We're moving our dials left and right at the same time and producing this diagonal motion. So how far did we move our horizontal dial and how far did we move our vertical dial? Well, if you reverse what I just said and ask the question, how far did we move our vertical dial and how far did we move our horizontal dial? Well, this right here, this would be the rise. It tells you how far up it goes. And this is the run. This would tell you how far up it went for a given distance horizontally. Or, as I say over here, tells you in a relative sense how fast you spun each knob. You spin the vertical knob faster than the horizontal knob, and you get a real steep slope. If you do it slower, you get a real shallow slope. Nice thing about this is we didn't have to make up new words that sound weird to you. Rise, well, that's pretty much what it sounds like, right? I mean, how far does a balloon rise? That tells you how far up it went. And if you're ever confused about which way is up, just unhook the strap on your watch and let go. The opposite from the way it goes, that would be up. You can buy those in sporting goods stores now, you know. Well, the ratio here rise over run. You could say that's up over sideways. This is a measure of the upness, and this is a measure of the horizontalness. And when you put it together, what do you get? You get a slope. Rise over run. And you haven't probably seen this before. That's a special kind of equal sign. That means it's equal because we say so. In other words, it's a definition. Rise over run. That is the definition of a slope. Pretty simple, right? Well, it's the cool thing about mathematics. Really simple concepts end up being the most important ones. Don't believe that? Well, actually it goes on. You'll be using these slopes in differential geometry. You'll be using them well before that when you learn about tangents. And that's why I said you'll probably use slopes for the rest of your life, because they're going to come up. They'll come up on site plans. They'll come up in other math classes. They'll come up in science classes. My brain isn't big enough really to remember all the places where slopes turn up, but they're all over the place. So what's the first thing you have to do when you've got something new? Of course, you have to find categories, right? You have to find some way to, you've got different types of things, so you categorize them. It makes it easy for you to talk about them. Well, you get slopes that go like that, and the way we're going to categorize them is this. We got slopes that are positive. We got slopes that are negative. We got slopes that are zero. And we got slopes that don't make any sense. There's only one of these here. And one of these don't make any sense kind. It's also called undefined. You could say it doesn't exist. And sometimes it's called infinite. Let's go through these one at a time before we worry about slopes that can't be computed. Among the three types that can be computed, there's positive, negative, and zero. Positive means that as you go from right to left, it goes up. Negative means that as you go from right to left, it goes down. Pretend that's a straight line, please. Do me a favor. Pretend that's a straight line. That is a downward slope. Why? Well, as you go from left to right, you're going downward. Here, as you go from left to right, you're going up. And what do you think zero is going to be? Well, that's when you don't do anything with respect to up or down. You go straight horizontal. All the motion is left-right. The elevation does not go up or down. It doesn't change. There is no rise, which means with a zero rise, you would get zero over whatever the run is. And as you remember from a long time ago, it doesn't matter what the denominator is. When the numerator is zero, the whole thing is zero. And that's your zero slope. Zero over whatever number you choose. It doesn't matter. Okay, so the four main types of slope. We just defined the first three, and they're pretty intuitive, right? And it's kind of what you'd expect, especially in our culture. We tend to go from left to right, so if it goes up from left to right, is it China or Middle East where they go from right to left? They might define slopes differently. If you're studying this in China and they say it's the other way around, don't argue with them. That's just the way they look at it. Well, what about this one here? This, we don't know what the heck it is. This is positive. This is negative. This is zero. Where do you think we end up with our, we don't know what the heck it is, slope? And that is the straight up and down. That looks nothing like straight up and down. Once again, humor me. Pretend that is straight up and down. That is a vertical line. Well, with the vertical line, what's the rise? Well, it's over the run. Now let's pick some section here. Well, let's say that section is 5 units up. Okay, there's 5. So there's the rise. So when we compute the slope, we get 5 over, and how far did we go to the left or right? Well, we didn't. It's just nothing. So it's 5 over 0. Oh, wait a minute. If you saw the end of the last video, you know what happens when we divide by 0. The universe explodes. We don't want that. So this vertical line here, we call it undefined. It just doesn't have a slope. We can't talk about it. Sometimes people will say it approaches infinity or it becomes infinite. Why would you say that? Because as this number gets smaller, down here, not 0, but real small, the result gets bigger. That's easy to see. Let me put a 5 down here. I put 0.1 here, and what do I get? 50. Okay. What if I get 5 divided by 0.01? Well, that's 500. And if I have 5 over 0.001, that's 5,000. As this number gets smaller and smaller and smaller, it becomes obvious that the slope just gets bigger and bigger and bigger, until you finally get to 0 when you say, wait a minute, we don't have a number that big, because you can't divide by 0. So if you hear somebody refer to that as infinite, that's what they're talking about. What they're saying is, as this number gets closer and closer to 0, the whole thing gets bigger and bigger and bigger. So our fourth category here is our category of, we don't know what the heck it is. We can't talk about it. It just doesn't have a slope. It's one of those underprivileged minds. It has no slope. Well, now that we know what a slope is, and we've categorized them, how do we actually find them? Now, let's see here. We don't really need the grid right now, I guess. So let's drop down below the grid and lay out a little bit of algebra. Now we've got x1, y1, and x2, y2. Those are 2 points. I don't know where they are. Doesn't matter where they are, because you're always going to find the slope the same way. You can go either direction, but you have to go the same way both times. In other words, we're going to subtract the y coordinates from each other, and we're going to subtract the x coordinates. We're going to take the difference between the y coordinates and take the difference between the x coordinates. The trick is we have to go the same direction both times. We can take y2 minus y1 and then x2 minus x1. We can take y1 minus y2, x1 minus x2. What we cannot do is take y2 minus y1 and then x1 minus x2. The only thing that will do is give you the wrong sign. Other than that, you'll be okay, but you'll have the wrong sign for the slope. You don't want that, do you? So, what you really get here is, say, we'll try it this way, minus y1 over x2 minus x1. If you have a coordinate plane, you have your given points, you're given these coordinates, you can always find the slope. Real easy. And there's a couple of quick facts that you need to know. Might have already guessed. Parallel lines have equal slopes. That's real important. It's a good thing to know, because later on when we do equations of lines, you're going to be able to instantly spot the slope of any line. I mean instantly. You'll be like a hungry cat. You'll know exactly what the slope of a line without even thinking about it. What else? Well, perpendicular lines their slopes, hard to write in shorthand, I'll just say that their slopes are negative reciprocals. Oh, that sounds like a big deal, doesn't it? Negative reciprocal. Negative reciprocals. What is that? Well, it's a lot easier than it sounds. If I've got some number b, the negative reciprocal is minus 1 over b. And that's true for any number. So if you've got the negative reciprocal of minus 1 over b, what would that be? That would be b. They go back and forth like that. The negative reciprocal of negative b would be positive 1 over b. So, parallel lines have the same slope. Perpendicular lines, the slopes are negative reciprocals of each other. There's another way you could write that. If you have two slopes, m1, m2, then you would write m1 times m2 equals minus 1. Some people would say it that way. But if you solve through for either slope, you multiply through by 1 over m2, and you get m1 equals minus 1 over m2. And from what we said a few minutes ago, or in the previous video, I bet you can already spot one important condition we have to put on these things. Yeah, not equal to 0. Neither one of these can be equal to 0. And the algebra makes that kind of obvious. There's nothing you can multiply by 0 to get minus 1. However, if the slope is 0, that means you just have a vertical line. And, oh gee, we have a vertical line right here, don't we? It's our y-axis. Actually, I got a whole ton of vertical lines, but let's try the y-axis here. Any other line with an undefined slope would, of course, be parallel. We already know. If they have the same slope, they're parallel. Now, if they're negative reciprocal, they're perpendicular. Every line except this one, you can algebraically figure out what the slope of the line perpendicular to it must be. This one, since it's undefined, how do you find the negative reciprocal of nothing? Or conversely, we have this one over here. Has a slope of 0. How do you find the negative reciprocal of 0? Well, this way gives you kind of a clue. Because 1 over 0 is not defined. But wait a minute. This slope here is not defined either. Minus 1 over 0 isn't defined, and neither is this. That's not a proof, not even close to a proof. But it shouldn't be too hard for you to remember that the perpendicular to a vertical line is a horizontal line, and the perpendicular to a horizontal line is a vertical line. Every other slope in the universe can be computed algebraically if you're looking for the perpendicular of the slope. Pardon me, the slope of the perpendicular. And of course, parallel, there's nothing to do. Parallel lines have the same slope. So once you find the slope of one line, you instantly know the slope of every line parallel to it. On the other hand, if you find the slope of a line and want to know the slope of every single line perpendicular to it, you take the negative reciprocal, unless that line is vertical or horizontal, and then you just have to know that if it's horizontal, the perpendicular is vertical, and vice versa. It sounds more complicated than it is. For instance, let's find the slope of the line connecting these 2 points. And then we can actually draw the line and see if what we did makes any sense. Let's call these x2, y2, and stick with our y2. In fact, if we use point notation, this is P2 and P1. That'll help us keep the order straight. So we'll do P2 minus P1 in the coordinate sense, of course. So we have minus 6, minus 2. That's the rise, right? Those are the y coordinates. Over minus 2, pardon me, 2, minus a minus 2. So we got this right. We got minus 6, minus 2. We've got 2 minus a minus 2. The slope is minus 2. What if we graph these? Let's see here. We got minus 2, 2. We've got 2 minus 6. So we got a slope of minus 2. How do we interpret that? That means that as we go 1 unit to the right, we drop down 2 units. Or you could say we drop down 2 units as we go 1 unit to the right. And does that make sense? According to our little drawing here, this is where we've got the points here, minus 2 and 2, 2 and minus 6. So here's the point, and here's 2 minus 6. We connect them with a line, and let's see what we got here. We go 1 unit this way, and 2 units down. 1 unit this way, and 2 units down. So it all makes sense. And this, as we go from left to right, goes down, and we have a negative slope. So everything we did makes sense. Son of a gun. Here's one of those error analysis problems. In fact, here's 2 error analysis problems. So we've got this person here. I'm going to assume that it's a reporter. I've maligned politicians and legislators enough. It's time to start on reporters. Seriously, if you've ever witnessed or been part of an event that made the news, and then read the account of it, or listened to the report on the radio or the television, most of the time I sit there thinking, where were they? That's not what I saw. That's nothing like what I saw. One of the best ones I ever saw was, there was a student demonstration in a town that I lived in, and I knew one of the people involved. His name was Vic Walker, not his real name. And he was a complete space case. I mean, if you asked him what time it was, you got a 15-minute lecture on temporal metaphysics. And everybody said the same thing. I mean, I didn't know anybody who really wanted to ask him a question. If they did, they just immediately hit themselves upside the head for being so dumb. Well, there was a demonstration on campus, and I read about it afterwards. The reporter wrote, "Student spokesman, Vic Walker." I read that and thought, no student ever named this guy to be a spokesman. He couldn't speak for himself, much less any other students. All the reporter did was find some weird guy who didn't make any sense and quoted him left and right and referred to him as a student spokesman. He wasn't speaking for anybody except himself and didn't do a very good job of that. So from now on, the people who make mistakes in these videos, I'll refer to as reporters. So we got this reporter here who thinks that the slope is 4 over 3. Now we have the rise right here, right? And here's the run. I'm doing this a long way. You probably already know what he did wrong. And what is the slope? The slope is rise over run. What did he write? Well, he wrote run over rise. You can't do that. You can't run around reversing these two. Yeah, think you're well aware of the difference between 4/3, which you get over here, and 3/4, which you get when you do it right. That are not the same thing. Not even close. And it could be worse. I mean, this could be 10/3, this would be 3/10, or 3/10. Yeah, flipping these two doesn't get you anywhere near the right answer. It never will. And that's what he did wrong here. Just be sure to keep that straight. And down here, he made one of those terrible mistakes I think I already told you about. He forgot which was 0.2 and which was 0.1. At least that's probably what he did. Let's see, here he's using this as 0.2 and subtracting this one from it, the top part here. So he's got 7 minus 5. Okay, that makes sense. Down here he should have 2 minus 4. Remember, you have to do it the same way both times. And what did he write? Oh, he messed up. He wrote 4 minus 2. So what would the right slope be? Just a negative of that. That's the problem when you reverse one of these. You'll just get the negative of the correct answer. Doesn't seem like a big deal, and if the only thing you're doing is computing slopes, your teacher might give you a lot of credit for that. However, finding the slope is frequently one step in a problem. And when you get that step wrong, everything that comes afterwards will be wrong. You might end up with no credit at all. That's kind of a drag because you got the right idea. So pay close attention and don't end up losing credit for some tiny little mistake that really should have only cost you a point or two, but since it's part of a much larger problem, it could end up costing you 5 or 10 points. It's not fair. It's just the way it is. The question here is, we have two lines, a line that passes through these 2 points, and a line that passes through these 2 points. Are these two lines parallel? Or are they perpendicular? Or are they nothing? By the way, that's the empty set symbol. It doesn't really apply here, but what the heck, I had to write something down. Which one are they? Parallel, perpendicular, or just nothing? Easy way to find out. Let's compute the slopes. Hey, that happens to be the section we're studying, isn't it? Well, that's a coincidence. Suppose we arbitrarily take these as P2 over here and these as P1 over here. Why did I write that on top? Because I get confused easily. So, we're going to go P2 minus P1. So we have minus 2 minus 1 over minus 7 minus a minus 3. That would be minus 3. Will be minus 7 plus 3, which is minus 4. And that equals 3/4. And that's the slope for line 1. Okay, what about line 2? Well, make sure to keep this straight. We got 4 minus a minus 1 over 8 minus 2. Minus a minus 1 is 4 plus 1, which is 5. 8 minus 2 is 6. That's the slope of line 2. Well, if they have the same slope, they're parallel. If they had the negative reciprocal, which in this case was 3/4, so for L1 parallel to perpendicular to L2, then the slope for L2 would have to be what? Negative reciprocal of that, which would be minus 4 over 3. And just to double check, let's make sure I did not make an arithmetic mistake here. 4 minus 1 is 5, 8 minus 2 is 6. Yeah, I don't think I made an arithmetic mistake. Just to double check, guess what we're going to do next? We're going to graph these 2 points and see what the two lines actually look like when we connect them up. So we get these two slopes here. There seems to be no relationship. Let's graph it. Well, one problem with this graph, I guess any graph, is that 3/4 isn't all that much different from 5/6, is it? So they almost look like they're parallel. That's where the algebra comes in handy. The algebra says they're not parallel. They don't quite have equal slopes. If you just glance at these two lines, you go, yeah, they look parallel to me. And they do. But then 3/4 and 5/6 are only a slight difference in slope. So you got to remember your eyeball may not notice a slight difference of 2 or 3 degrees in the angle of these lines. Say the angle it makes with the horizontal, perhaps. And remember, if it doesn't make exactly the same angle here and here, you could, if these were parallel lines, then you could call the x-axis a transversal, couldn't you? And what do we know? Corresponding angles would be equal, which means that it would intersect the x-axis at exactly the same angle. And it looks like it does, but it doesn't. The algebra tells us it doesn't. Now, let's see if we can graph a line when all we know is one point and the slope. I bet we can. Let's try it. 0, 5. X is 0, y is 5. It puts us right there. The slope is 2/3. It's positive, so it goes that way, up. And what does that say? Remember, rise over run. Which means that if we go up 2, we should go across 3. So there's up 2, across 3. Boom. There's our next point, which has to be on the line. Now we want to draw that line. What we can do is, wow, it's the straightest line I ever drew freehand. Draw a line through the 2 points with the appropriate slope, which, as I say, we figured out by going 2 up, 3 across, 2 up, 3 across. See? Very easy. Okay, we've found slopes and we know what they are. But there's a way to interpret slopes. Actually, there's many ways to interpret slopes. One of them is as an average. For instance, suppose we put t down here. This is the x-axis, and we're going to call that t. And over here is distance. So we have time versus distance. And suppose we start out here from some point. Who cares? It's your library, your home, your school, it doesn't matter. It's some point where you started, from which we can measure distances. And let's say that this is laid out in minutes, and this is laid out in hundreds of feet. Okay. So let's say you walk 100 feet in a minute. Yeah, it's not fast, not slow. I don't know what that is. But suppose you did that. Then a graph of distance over time here would be like that. Suppose you just kept doing that. 100 feet every minute. Remember, these are in hundreds, so let's write times 100 on each of these. Times 100, times 100. So, what do we have from here to here? And here to here. Well, this went up 500. Remember, the scale is actually in hundreds. It's not a very good scale. Actually, if I was going to make this 100, then it'd have to be way, way up at the, way beyond the top of the page, and it'd be hard to see. So, this went up 500 units, 500 feet. This went 5 minutes. This is feet. This is minutes. And that gives us a slope of 100. And if we want to attach units to it, and it's feet per minute. There we go. Sort of cheek whiz. Anyway, that's awful. Pretend that says feet per minute. We got this straight line here, which means that it was traveling at 100 feet per minute all the way. Suppose he didn't do that. Suppose he just took away. There are times when he rested, and there are times when he went fast, and so his actual distance covered looks like that. Sometimes he was going real fast. Sometimes he was hardly moving at all. Sometimes he might have even been stopped. If we connect the starting point and the end point and draw this straight line, the slope of that line is his average speed. In one case, his speed never varied. He just plodded along at exactly the same speed for 5 minutes and went 500 feet. In this case, he went all kinds of different speeds. Who knows what he was doing? But he wound up at the same spot. If we connect those 2 points and compute the slope, that will give us his average speed. And this is true in many, many, many cases, and even more than that. You've got curves which show the relationship between some aspect of a process and the other aspect. In this case, the process is travel, and the 2 variables are time and distance. Oh, it could be temperature versus length. Some things expand as they get hotter. It could be lots of things. And those things will not necessarily move right along at exactly the same rate. You'll see curves. But if you want the average rate, all you have to do is connect 2 points anywhere. For instance, halfway through the trip, he was right here, right? Well, that puts him here. Well, let's forget halfway. Let's say 2/5, 40% of the way through the trip, he was right here. That put him here. If we connect those 2 points, we get an entirely different line, don't we? Now, what's up with this line? Well, this line is 300 feet this way and 200 that way, or pardon me, 2. So this new slope is 300 over 2, or 150 feet per minute. So 40% of the way, his average speed is way higher. And it has a lot to do with this real steep slope right here. It looks like he was definitely sprinting for about half a minute because he just took off right there. And then he got tired and slowed down. And then he made one quick sprint for about 20 seconds right there and sped up a bit. And that was it. So right here would be his highest average, or at least higher than the others, and it looks like it would hit the highest point right about here. You want to know where the highest average was? Just start at the beginning and figure out what you would draw a line to get your steepest slope. And it looks like it'll be right in here somewhere, doesn't it? So remember that. The slope between 2 points will give you the average of the process between those 2 points. Well, that's one way to interpret the slope. Here's another. You can use slopes to make comparisons. Which car has the better gas mileage? Well, that depends on your point of view. I mean, if you're the one paying for the gas, you would say the best mileage is the one that uses the least amount of gas per mile. If you're selling the gas, I would say the best mileage is the one that uses the most amount of gas per mile. If you're selling gas, you want to sell it, right? Why would you want people to conserve it? I'm going to assume that this is taken from the driver's point of view. And we're going to say that good mileage is the best mileage. And fact, there's only two of them, and as you remember from English, the word best doesn't apply when there's two. There has to be three or more. Better applies to two. So, which car has the better gas mileage? These guys are really smart. They even know which words to use. From the point of view of the person paying for the gas. Well, gas remaining is up here. Distance driven is here. So, just draw this line sort of across here. Like that. When they hit equal points of gas remaining, well, this guy's gone way farther than this one, hasn't he? It's more than twice as far. So, this guy has the better mileage. It's just interpreting these slopes here. That's all you're doing. It's pretty easy. No computations or anything like that. Well, speaking of using slopes to find averages, son of a gun, here's one right here. And this is, again, very realistic. This is exactly what is done. And this is exactly the kind of situations in which it is done. Let's suppose we start 2000 just right here. It's arbitrary. And we'll count each unit as 1 year. So this will go out to 2006. Now these numbers here, let's see, our top number is 15,400. Oh, darn. There we go. I've just labeled the vertical axis as 2,000, 4,000, 6,000. You're probably familiar with the K. That's old computer terminology. It doesn't mean kilo, it means thousand. Sometimes it does mean kilogram, but right now it means thousand. What we're going to do is go from 8,500 in 2000. So here's where they were at in 2000. Out here in 2006, 15,004. Well, we'll make it about right there, right? Now, well, pardon me. So if we lay this out, say each one of these lines is $2,000. Each one of these is a year. We start at 2,000 here, not zero. That would need too big a page for that. This is the only part we care about from 2000 on. When we compute the slopes, even though we've got money on this axis, years on this axis, and the scales aren't even the same, and this line would really be, if it was scaled properly, who knows. But what really matters is the differences. That's why this works out so well. What would the average change be? Well, it's the slope of this line. And what is the slope of this line? Well, here's the point, 2006, 15,400. So let's start our y2 minus y1 as 15,400 minus what? Well, 8,500 down here, right? And that, we have 2006 minus 2,000. Well, I'm just going to put a 6 down there. It seems kind of obvious. Okay. So when we work this out, we get 6,900 over 6, or $1,150 per year. And if you check this out, that makes sense. But remember, that's the average. This straight line here, this is not intended to be any kind of representation of reality. This point right here, this is real. This really happened. This is what the profits were in 2006. And this point here, this is real. This is what really happened. But what happened in between, we don't know. Their profits could have dropped. I mean, suppose they just steadily lost money. And then they just all of a sudden got some new CEO who was on fire. And boom, they just started making money hand over fist. This was their average. That doesn't mean that the last 6 years were pretty easy and consistent. In fact, for part of those 6 years, they probably thought they were going to go out of business. Profits were dropping and dropping, and then finally came back to where they were almost 4 years ago, and didn't start going up. But when they did, they just flew. That could have been what happened, or it could have gone like this. It could have gone up, and then just leveled out. Suppose it went up drastically for some reason, and then just didn't change at all. Both of these are equally possible. There is no way to choose between them. In fact, there's a certain concept of reality that would have to work its way in here somewhere. But theoretically, there are an infinite number of ways to connect this point with this point, and they're all possibilities for what the actual curve might be when you graph year versus profit. But there's only one straight line connecting the beginning and the end, and that straight line will represent the average. Well, when I say that, what I mean is the slope of this line will represent the average. And if you want to look at it that way, the slope does show an increase of 1,150 each year. So if you want to graphically show a steady increase as the average, well, this would be it. But whether it actually grew that way or not is very unlikely. Normally what you do is you would have data points, say every 6 months, and there'd be a point here and a point here, and you would connect them smoothly and try to figure out what happened year by year. But we've got 2 data points fairly spread out, connecting with a straight line, and we get the average. Okay, here we are interpreting lines again. And I say this is, well, like I said before, slopes are going to keep coming up in all kinds of things, and here we are using them in data analysis. That's another place where you're going to see them all the time. So, during which 5-year period did the NBA attendance? And this is not an uncommon way to graph things. So we've got one color line for NBA, we got one color for NFL, and they even put little footballs and basketballs, and I guess those are pucks. They should have put maybe a guy with a face mask and blood on it or something. Anyway, we got the NHL down here, and this. How about a guy smiling with no teeth? That'd be a perfect hockey icon. During which 5-year period did the NBA, that would be this one, attendance increase the most? Well, remember the increase would be the part where the rise over the run is the highest, and that would be the steepest, right? Just have a nice, simple, intuitive idea of steep. You would probably say that's more steep than that. And you'd be right. Easy way to define steepness would be the line with the highest absolute value. In other words, that's a steep down slope. It's more negative than this one. The one with the highest absolute value, that's the steepest. So even though this is negative, it's steeper than this. Okay? When did it increase the most? Well, boom, I would say 85 to 90, wouldn't you? There's that real steep jump. In fact, it went from, let's see, attendance. So what's that, like 1,300 up here to about 2,200? Whereas none of these jumps are anywhere near that size. So, up here, for the NBA, that's obviously 85 to 90. The rate of change for this 5-year period. Well, again, that's not too bad. What did we decide this was? We already know it's a 5-year period, right? It's rise over run, and we know the run is going to be 5 years. We can just put that there, right? We don't even need to subtract these. They're already telling us it's a 5-year period. So, what's this? Well, let's just say that's 1,200 and that's 2,200. The difference is about 1,000, isn't it? So, that's a way to write approximate. 2 squiggly lines. Remember, that. It's congruent. You got the equal sign with a squiggly over it. Well, two squigglies together is like approximate, almost. And that's, wow, 200. That's a steep slope, isn't it? However, that's the slope that would exist if these were in scale. Remember, this is 5 years for this distance here, but this attendance in oh wow, millions? Ooh, jeepers. Well, that's 12. Million. 22 million, which is 10 million. And this is $2 million is the slope, approximately. That's a steep slope. In other words, it went up 2 million people per year. That makes sense. In 5 years, went up 10 million. That's 2 million per year. 2 million times 5 is 10 million. See? Even when I make mistakes, it still makes sense. Now, during which 5-year period did the NHL increase the most? Yeah. That's the one with this one here. Well, I would say that looks like the steepest slope to me, doesn't it? I hope it looks that way to you too. So that's 95 to 2000. And what was the rate of change? Exactly the same as the slope. So the slope here, well, that looks like, remember we can put 5 at the bottom, right off the bat. We already know that it's a 5-year period, so they've told us the run is 5. What's the rise? Well, we went from, what's this, 18? So we went from 5 million to 18 million. Wow. Just write 8 million. Let's forget all those dumb zeros. 18 million minus 5 million. In fact, I got a better idea. You probably haven't seen this before, but for the sake of laziness, let's do it. A million is 10 to the 6th power, so if I write 18 times 10 to the 6th, that's 18 million. And I can subtract 5 times 10 to the 6th. There's a name when you do it that way, but it's not our job to know that right now. So this is 18 million, this is 5 million, so we get 13 times 10 to the 6th, that's 13 million over 5. And I can just write that as 13 million divided by 5 is 2.6 million. You can just read times 10 to the 6 as million. The attendance went up 2.6 million per year. Wow. They must have been giving away free cars with every ticket. Well, let's see. How do we interpret the line graph for the NFL? It's almost linear. Well, what it means is attendance increased steadily. Here you see it was a little bit and then it dropped and it went up. This almost straight line implies a very steady increase. There were no large jumps in either direction. That's all that means when it's fairly straight. Straight line, you could also say, implies consistency. Well, things jump around like this. Who knows what's going to happen in the next 5 years? I mean, you got the 5-year period did that, 5 years did that, another 5 years did that. Like, gee whiz. This, well, the NBA jumped here, but then became consistent over a 10-year period, so you got a little bit of consistency. Here, you got extreme consistency. You can have a reasonable amount of confidence in just projecting that it's going to be just a little bit more in the next 5 years. It won't be up there and it won't be down there. It'll probably be right there because These last 4 data points are a pretty good predictor of the 5th one. But I think the correct one-sentence explanation would be that the increase has been steady and fairly constant over the last 15 years. Boom, you're done. And here's an interesting problem. Our job is to find 2 values of k. Well, let's start by finding 1 value of k. When we figure that out, finding the second one will probably be kind of easy. What does it mean to be collinear? Well, it means they're all on the same line. So what we would really want right off the bat is we'd want the line connecting 3, 1, 0k, and k5 to all have the same slope. So we'd have 3, 1, and 0k and compute that slope. 0k and k5, that slope. We could also compute 3, 1 and k5. For instance, let's try it here. A simple picture of what we're talking about might help. Here we have minus 3, 1. Here we have 0, k. We don't know what the actual y, we don't know what the y coordinate is. So just try a little. Here it goes up or down. We don't know where it is, but we know that it's here at 0. And this, well, we know we're up here at 5. Oops. Up here at 5, but we don't know. Pardon me. What is it we don't know again? Can't see that part. Yeah. So we have 1 point here. We have a point that's going to have a 0 on it and a k up here somewhere. Now we have a point that's a 5 here, but it could be anywhere along here. Seems a little confusing, doesn't it? Well, let's see what algebra will do for us. That's, for instance, the slope between these two. What do we get? K minus 1. 0 minus a minus 3. Or k minus 1 over 3. For these to be on the same line, they have to at least have the same slope connecting them. So let's check the slope from 3, 1 to k5. Well, we'll call this point 2. So that'll be 5 minus 1. 5 minus 1. There's our change in our y coordinates, which is the rise. And we have minus 3 minus k. And that equals k minus 1 over 3. Naturally, the idea is to find the simplest equations you can to solve any particular problem. Now this bunch down here that I was going to set equal to this, oh, pardon me, that doesn't make any sense. I think the 2 slopes that make the problem easiest is to take the slope from 0k to k5. So we have k minus 5 here. And just plain so the slopes that lead to the simplest equations are to take the slope between this and this, k minus 5 over 0 minus k, that's k minus 5 over minus k, and set that equal to the slope between these two, which is k minus 1 over 3. You set those equal, and remember, that means that times that equals that times that. We remember the old cross multiply and set it equal. So we get 3k minus 15 equals minus k squared plus k, minus 1 times a minus k. Do a little rearranging here. We add k squared over here, subtract k, subtract k from each side and get plus 2k, and minus 15 just stays right where it is. So what do we do? Well, let's see, what are factors of minus 15? So I think we can rewrite this, or factor it as, and let's see, 3 times 5, and the difference between 5 and 2, 5 and 3 is 2. So I think we're on the right track. If we have something like x minus 3 times x plus 5, what do we get? Let's see here, we get minus 3x plus 5x, that'll give us the, and I shouldn't have used x's here, it's just the way I'm used to factoring polynomials. These are actually k's in this case. So this is k minus 3, and this is k plus 5. So we minus 3k plus 5k, that'll give us our 2k, minus 3 times 5 is minus 15. So the possible choices for k are that k equals 3 or minus 5. What happens if we punch those in over here? Let's take a look. Here we had 0k. And what were our two choices? I better write them down where I can see them. 3 and minus 5. So it could be 3 or it could be minus 5. 0, 3. Oh, there's a 3. And 3, 5. So we move over here and then up to 5. Hey, well, that looks like it fits, especially if I could draw a straight line. That would work real well. What about minus 5? Well, here's 0. Minus 5. And minus 5, 0. And this is wrong. It's not minus 5, 0. It's minus 5, 5. Looks a little better. Which means here's the other line that passes through. Are these two perpendicular? What do you think? You know, they almost look like they are, don't they? But let's take a look and see. We got a minute. When k is 3, we've got the line 3, 1 and 0, 3. So what would our slope be? Well, I would say it's minus 3, minus 1, 0, minus 3, over 0, minus 3, which is just, of course, minus a minus 3, which, of course, is a plus 3. So we have minus 4 over 3. What about when k is minus 5? Over me, I should have done it like I knew what I was doing. K equals 3 leads to this. What does k equal 5 lead to? Pardon me, k equals minus 5. What does that lead to? Minus 5 minus 1. Sorry, that's, there we go. Minus 5 minus 1. 0 minus a minus 3. We get a positive 3 at the bottom here again. Minus 6 over 3. That equals 2. 4. These two to be perpendicular. One of these, if this is 2, the other slope would have to be minus 1/2. Minus 4/3 doesn't work. So even though when we drew them, they kind of look like they're perpendicular. Didn't seem to work out that way, did it? So that's the end of our super long video on slopes. And in fact, we're going to do more equations using slopes